Namaste everyone, welcome to my class. I am Vinod. So we are in physics, chapter 10 gravitation. Universal law of gravitation is also known as inverse square law. So why did the name inverse square law is related to universal gravitational law? So inverse square law means in universal gravitational law we have force is inversely proportional to the distance square. Since force and distance are related, that is distance square is inversely related to the force. When force increases by, distance between the two bodies is doubled. So if we have increased the distance between the two objects, for suppose I'll take the example, two objects are separated by distance d. For this we are going to make a relation the force of attraction between them as 1 by d square. If we have double the distance between these two bodies. So right now we have the distance, the new distance is d prime, which is equal to 2 times of the original distance, twice the original distance. If we have taken this case, masses we are not going to change, but how the force of attraction between them is related. So F is inversely proportional to 1 by d prime square, the new distance between them. So the new distance is nothing but 1 by twice the distance, twice the original distance between them. So if we take the square of this, so F is proportional to 1 by 2 square, we have 4 and then d square. So here F is inversely proportional to 1 by d square. Now if you check here, we have this number 4. That means if distance is increased twice, the force of attraction between them is going to reduce 4 times. Since it is inversely proportional to the square of distance between the two objects, the force of attraction, so it is also known as inverse square law. So we have come to the concept of free fall. If any object falls freely only under the influence of gravity and no other force acts on it, we call it as free fall. In our life we see many examples like the Newton example where the apple got detached and fell down from the tree. So no one threw it, it fell only under the influence of gravity. Such a fall is called free fall. The raindrops the rain which comes down, it is also free fall. Whatever the objects, if they fall, only free fall means falling freely. So it is falling freely. So I'll draw this apple example. So no one detached this, no one pushed it down. After it got detached, it fell freely only under one force, that is nothing but the gravitational force of the earth. So all the bodies which fall freely only under the influence or due to the gravitational pull of the earth are said to be in free fall. So when they are falling freely, we know they are going to come down with an increased speed, accelerated speed. Now there is a bit confusion between the lighter objects and heavier objects. People in the olden days believed that the lighter objects are, when they reach the earth, though all the objects lighter and heavier are in free fall, lighter objects will travel with less speed and the heavier objects are attracted by the earth so that they accelerate more and they fall down at a higher speed. But it was proved wrong by Galileo Galilei. So in order to prove that all the objects reach at the same time or all the objects which are in free fall experience the same acceleration, Galileo Galilei, what he did is he went to the top of the Leaning Tower of Pisa. So this is Leaning Tower of Pisa. So what he did is he dropped all the 3 balls or metallic spheres. When he dropped, he found that all the 3 reached the earth at the same time and the change in velocity is equal. That is, they suffered or they experienced uniform acceleration. So the acceleration is uniform in all the bodies irrespective of their masses. But what is the reason for the lighter body to reach, like if we try this with a paper and a pen, we will find that pen reaches faster than the paper. Actually both paper and pen should experience the same acceleration, but why it is not happening so? It is not happening because of the air resistance. If we completely remove the air, then all the objects, when they are, whether they are heavy or lighter, when they are left, they are going to reach the earth at the same time with the same speed, and they experience or they undergo the same acceleration. After, when Galileo did this, he said the difference in the speeds experienced by lighter bodies is only due to air resistance. So to pull away the air completely, later on Robert Boyle invented a vacuum pump. With the help of this vacuum pump, what he did is he took a glass container, and from the glass container he has inserted one lead bullet and another one is a feather. This is lead bullet, which is heavy, and another one is a feather, bird feather, that is the lighter one. Actually if we see, the feather will take so much time to reach to the surface. With the help of vacuum pump, he pulled out all the air from within this glass jar, completely made it vacuum, so there is no air resistance inside it. When he opened the clips, both the bullet and the feather reached to the bottom of this container at the same time. So it is very much clear that all the objects, whether they are lighter or heavy, they are going, when they are in free fall, they experience the same acceleration. When they are left at the same height, they will reach to the ground at the same time. Their velocity when they touch the ground is also the same. So as we have seen, all the objects, when they fall to the earth, they experience the same acceleration due to the gravitational pull of the earth. We call this acceleration experienced by the freely falling bodies as acceleration due to gravity. So this is the acceleration where when an object falls freely, only under the influence of gravitational force, the acceleration experienced by it is called acceleration due to gravity, and it is represented by small g. So in order to find out the equation for acceleration due to gravity, right now we are going to consider a mass on the surface of the earth, not too much height, at very little distance from the surface of the earth, or you can consider an object on the surface of the earth. So when it is on the surface of the earth, we are going to imagine earth as a sphere, spherical in shape. When we consider a sphere, the entire mass of a sphere appears to be concentrated at the center of the sphere. So for any object, when we are calculating the gravitational force, we have to find the distance from the line joining the force axis, the line joining between the centers of the two bodies. So the distance between the centers we are going to measure. So since earth is spherical in shape, the center of mass appears to be exactly at the center. So from this point to the surface, we take it as the radius of the earth. So this is a negligible height. Right now we are not going to consider this height because this height is very much smaller. Maybe it will be in meters or kilometers, but the radius of the earth is 6,400 kilometers. Compared to this distance, whatever the height which we kept is negligible. So according to universal law of gravitation, the force experienced by this object, the gravitational force experienced by this object can be calculated with the universal law of gravitation, F equal to G. I wrote this one as small m, the mass, and this will be the capital M, G mm by the radius square. Radius square is nothing but the distance from the center of the earth to the object which is on the surface of the earth. Now, whenever this object is left, it is going to accelerate. The acceleration force is also because of the gravitational pull of the earth. According to Newton's second law, we know this force is related to F equal to ma, where this acceleration will be produced by the force. So since we are considering the acceleration of the object when it is falling freely is due to the gravitational force, so here we are going to consider the acceleration as acceleration due to gravity the same gravitational force, and we have an equation for gravitational force. Both are the same forces acting on the body, same force acting on the body. So we will equate those two equations, so to find out the value or the equation for G, small g, capital G r square. So mass on both sides will cancel, mass of the object. So small g equal to gravitational constant is always constant, mass of the earth by radius square. So from this equation, acceleration due to the freely falling bodies does not depend on the mass of the object which is left. So we have seen it, and practically it is also proved, whether the object is heavier or lighter, acceleration due to gravity does not depend on the mass of the object. But on what factors does it depend? It depends on the mass of the earth and the radius of the earth, or the distance from the center of the earth. On those two factors it depends. So now we will find out the value of acceleration due to gravity by substituting the known values here. So on the earth we have all the bodies which fall will experience the acceleration due to gravity, small g equal to universal gravitational constant 6.67 into 10 power minus 11 Newton meter square per kg square. Then we have the mass of the earth 6 into 10 power 24 kilograms, and then the radius square of the earth, it is 6.4 into 10 power 6 meters, so whole square. When we take all the units, you are going to get units in terms of meter per second square. So after solving this all values, we will get the value of small g or acceleration due to gravity as 9.8 meter per second square. That is the acceleration due to gravity which is experienced by all the objects which are on the surface of the earth. Okay, variation of acceleration due to gravity on the earth. We'll take the first point. We'll go the first point. It is on the surface of the earth. So near the poles. Earth is not exactly the spherical in shape, but it is little oblong, where near the poles it is little flattened. So the distance from the center to the poles, that is from the center, the radius of the earth is, there is little difference in the radius of the earth between the equator, that is measured at the equator, and that is measured at the poles. Almost the difference is 22 kilometers, not too much, but little less. Then also, since we have the distance denominator, the distance in the denominator, the radius in the denominator, the square of the difference will make it maximum. So when we are squaring it, so when the number in the denominator decreases, as a result, the whole fraction will have a higher value. So as this value in the denominator decreases, the acceleration due to gravity increases, is little higher at the poles, so it is more at the poles. When we go to the equator, at the equator the radius of the earth is maximum, so denominator is more. When the denominator is more, as a result we will have for the fraction a less value. So here near the equator it is little less when compared with the acceleration due to gravity that is experienced by a body at the poles. So that difference you can notice, no? So it is the difference, that is the radius of the earth varies with the poles, at the poles and at the equator. So it is acceleration due to gravity is more at the poles and it is less at the equator. At the altitudes, the value of g at the altitudes. Now altitudes are if the body is at a height greater when compared with the distance from the center of the earth, or if you are going for a height which goes up to 1000 or 10,000 kilometers, at that time we have to consider the height from the center of the earth. We have to include the radius of the earth as well as that height. As a result, in this formula g equal to gm by r square, the denominator increases. As there is an increase in the denominator, we are squaring it, the value of the fraction decreases. So when we go to altitudes, the acceleration due to gravity decreases. As we go up, the acceleration due to gravity decreases. Now, when we are going to depth, so we have to be very careful, though there are equations to solve. Right now I'll explain you based on the concept. When we are going into depth, I have dug a hole and took the object here. Now the object is here. When we check, what we find is F equal to G M by this small distance. I'll take this RD, that is that small distance square. Before I said if denominator is decreasing, definitely the fraction value should increase. But check with the mass. Right now when we go inside, little inside, the outer mass, I mean the gravitational force of the earth for the boundary which is outer, so this will not play any role in attracting the body. So this force will not be acting on the body because of the mass. So we will not be attracted from the center. We have gone to a depth inside. So now our new distance from the center is RD. So RD is smaller than the actual radius of the earth, but for this small radius, the mass of the inner sphere will be very much less. So as mass decreases, so we have new mass here, I'll write it as m prime. So new mass for the small sphere, so mass is less. Even though the denominator is increasing, there is a decrease in the mass. So as a result, the acceleration due to gravity decreases as you go inside. So when we are going into the inner part of the earth, so what happens now? Even the acceleration due to gravity decreases because the mass of the smaller sphere is very much less. Once we enter into the center of the earth, once we reach the center of the earth, right now the acceleration due to gravity completely, G value will become 0 at the center of the earth. So we feel weightlessness. So there will not be any attraction at the center of the earth. Thank you very much everyone. We will meet in the next class with the equations under free fall and mass and weight, difference between mass and weight. Thank you so much.